Welcome to Mr. Frolic's physics classes. In this class, we're going to talk about work and energy. Hello there. Today, we're going to continue talking about our studies of energy. And we're going to start to bring our focus back to our mechanics. So we're going to actually talk about mechanical energy. Now, let's remember that mechanical energy or mechanics is the study of motion. And therefore, mechanical energy is actually somehow related to energy of motion. And initially, let's just call this kinetic energy. Kinetic energy. Usually, kinetic energy is represented by the symbols we represent by Ke or E index K, which I don't really like, I hardly ever use, but IB uses this one, or with my AP classes, just K. Okay? So these are the main symbols. Now, let's consider the following situation here. We have a table, and then we have an object. It could be an eraser or a box or a rock, something sitting on that tabletop. Would that rock sitting there as it is, does it have any kind of energy of motion, of kinetic energy?
No, it doesn't have energy of motion.
Exactly, it doesn't. But what if now I grab this eraser and I toss it? Okay, so I'm now making this eraser move in air. Does it have now an energy of motion?
Yes, now it does have energy of motion. When you grabbed the rock and tossed it, energy was transferred from your body to the rock.
That's interesting. So now it does. If by any chance this here is heavy enough or is moving fast enough, and for example, it strikes some kind of glass surface, it could break that glass surface. So it can cause changes on it. That's cool. Now, what was needed from when I did, well, my initial situation of not having that energy of motion to now having that energy of motion? What was needed for that energy to be transferred into my object?
We need an applied force.
A force. That's an interesting perspective. So if I just push down on it, like this here, force of the hand on the box, would that be enough to actually produce the, to transfer energy to the box?
No, you need the applied force to make the object move.
So that's a great idea. So what you mean is that to transfer energy, we need to have a force acting over a displacement. Okay? So to transfer energy from one object to the other, or to transfer energy into an object, what I need is to have a force acting over a displacement. Let's see this in more detail. So we can have the following situation. Here's an object displacing this way, and let's say that the applied force is in the same direction of motion. What is happening here?
Since the force is in the same direction of the velocity, the object is speeding up. I believe that the energy is increasing.
That's right. This object is speeding up and therefore its kinetic energy is increasing. So the change in energy is increasing. What about this next situation? Object is moving. This is my displacement, but now the force is in the opposite direction. What do you say is happening?
Well, now force and velocity are in opposite directions, the object is slowing down. This means that the energy is decreasing?
That's right, exactly. Now this object is slowing down. And the change in energy should be somehow negative. That's okay. Let's consider a third situation. Something more like this. Okay? This here, the situation could be, for example, a block sitting on the floor, and I'm making it move sideways, and this force would be, for example, the normal force. But anyway, it is a force that is at 90 degrees with the displacement. What's happening now?
The force is neither in the same direction, nor in the opposite direction of the velocity. I guess the speed of the object will not change. Is it possible that the energy does not change as well?
Exactly. The speed does not change, and therefore, the change in energy caused by this force is zero. Notice then this here. If the force is in the same direction of the displacement, I'm going to have a positive contribution to the energy of the system. This force is pumping energy into the system. So this force pumps energy into the system. If the force opposes the displacement, I would actually have a general effect of reducing the energy of the system. So the effect, the energy contribution of a force that opposes the displacement is to reduce energy of system. Now, if the force is perpendicular to the displacement, it's neither pumping energy into it, which is my first situation, nor removing energy out of it, which is my second situation. And in that sense, this force here does not make any contribution to the energy of the system. So a perpendicular force doesn't change energy. Now, please note this. I'm not saying that this force is not important. If I'm running on a tabletop, or if there was no tabletop for the box to run over, this object will actually, of course, follow a different path. So every force is important in the system. The only thing I'm saying is that when the force is perpendicular to the displacement, it does not contribute to the energy of the system, but it will play other roles. I would also like to point out that in our general/grade 8 physics class, I'm going to limit my discussion to forces in the same direction of the displacement, in the opposite direction, or perpendicular. In honors physics, we will discuss the situation where the force exerts a certain angle with the displacement. So that is for the ones who take honors physics in the future. So from the last screen, we have that when the force is in the same direction of the displacement or of the motion, the energy contribution is going to be positive. When the force is in the opposite direction of the motion, the energy contribution is negative. And when the force is perpendicular to the displacement, the energy contribution is zero. So what we need now is to define a mathematical operation or a new quantity that will measure how much of this energy is being transferred in or out as the force acts over a displacement. And we're going to call that work done by I want to put here into parentheses, constant force. So this is a new operation that we are defining right now, and that is going to be defined as, we're going to write this to here, so the work done by a force from A to B as being, in our simplified definition, plus or minus force multiplied by displacement. Okay? And the choice of the plus or minus should follow this idea here. So plus is if force has the same direction as displacement, which will give me a positive work. The minus should be if force is anti-parallel to displacement. They are in opposite directions. And then that will give me work being negative. Be very careful, because if force and displacement are perpendicular to each other, then we would have no contribution, work would just be 0. Now I find this name here, work, perhaps one of the most unfortunate examples of names that we gave to things. Reason is this here. When we say that something was a lot of work, what idea comes to our mind? We could just do this here. If I just hold this eraser here where it is, I don't move it at all, how much work am I doing to keep it there? If the displacement is 0, the amount of work done is 0. But if this eraser was any heavier, or if I just keep holding it for a long time, well, there's a lot of effort going on in here, but no energy transfer is happening. Okay? So let's please keep this in mind, that work for us really means just energy transfer. Now, finally, let's talk about units, because no physics lecture is complete without, I guess, an equation and some unit analysis. We have already seen that the unit of energy is a joule. But now we are defining a joule as force multiplied by displacement. So we have that 1 joule is going to be equal to 1 unit of force is Newton, multiplied by displacement, and the international unit of displacement is meter. But now, let's remember that 1 Newton from Newton's second law is equals to 1 kilogram times meter per second squared. So this is going to be 1 kilogram meter per second squared, multiplied by 1 meter. And so what we have is that 1 joule in fundamental units is 1 kilogram. Meter times meter becomes meter squared, divided by second squared. And what we should do now is just practice some problems to get some fluency with these new ideas.